So let's go back and take a look at this blog here. So let's see here. So whose blog is this? This is the Scientific Worldview blogspot.com. So is this a blog that, this is someone else's blog then, right?
Yes, this is on my blog. It only contains my conversation with the scientists over there. I am only a follower in that blog. The main scientist over there is Dr. Glenn Borchard. I am only a follower.
Okay, so this is your question here. So you are claiming
and I had a conversation with him which he posted on the blog.
Okay,
that
so this is the conversation you're having. So so you're the one who claiming that the universe contains many collections of galaxies instead of one. Is that true?
Yes, that is what is scientifically possible, because see, our atmosphere, the air around our planet Earth ends at one point, because any form of matter has to end at one point, at one place. I mean, it's proven that we cannot see anything beyond 13.8 billion light years. That is scientifically proven. That is why I am making this claim. Hello?
So so you wanted them to look into this matter that
hello.
Yes, hello. You wanted to look into wanted him to look into this matter that you think that the ether is
yes,
extends only as far as the collection of galaxies, and outside
and yes,
there's nothing.
Yes. Matter can exist, solid matter can exist anywhere, but any form of matter, like if you say air, water, ether, everything has a finite size. Even a solid matter also has a finite size. Even liquid water, or even gaseous air, or whether it be ether, everything has a finite size. Nothing can occupy the whole universe. This is what our common sense says.
Well, let's see. His response.
That is why I'm making this claim. And he said that it will be. I am hypothesizing it isn't foreign.
Well, it's kind of like
GC
See, your response here from GB is that he's taken that into the question of why is it we can only see 13.8 billion years. That's just the limit of what we can see. Although I'm thinking what you're saying is even further than that, that it's not really an observational limit, but that there's going to be a hard limit somewhere.
Beyond light years.
So, but
because see, if there is no ether, there can be no light. Because light is a wave. And if there is no light, how can we see anything over there? If there is no light over there. That is why I am saying.
Well, I don't know that what you're proposing could ever be, well, I suppose it could be proven if we had a really, really good telescope and we knew that it could see beyond a certain point, but yet we cannot see anything past that point, I suppose.
Yes, he is saying that the James Webb telescope will be launched in March 2021. With that, we can test.
Well, so all we can do is look
that
at
is
better
what
and better telescopes.
Dr. Glenn Borchard is saying, that that yes. Hmm.
So my
Yes,
opinion on this is that what he's responding to you with, which is the announcement of the James Webb Space Telescope, is that let's
yes.
see, is this a prediction? Is that we will soon find cosmological objects older than 13.8 billion years?
So that would be older than the
Million
universe.
light years. Actually,
Uh,
even if there are any cosmological objects for that, there if there is no light, we yes. See, actually, the universe is infinite. The Big Bang theory is actually wrong. It has been proven by Dr. Glenn Burchard that the Big Bang theory is
well, that's certainly one of the predictions if the
and
Big Bang Theory
see
is wrong.
even
Now, the James Webb Space Telescope is specifically designed to find things which are normally invisible in the visible range, and I believe the infrared range, because things get redshifted. So,
see if
I
there is no light.
now let's see. Now, first of all, I'm having a hard time understanding you.
Yes.
So you might want to put your comments in the chat. And
Okay.
I'm thinking, please wait until at least I finish my sentence, because I really can't get out anything but when you keep on talking over me. Okay, so I'm trying to just comment on what you're saying, and when you talk over me, that interrupts
Okay.
me, and I
Okay.
can't
I'm not
complete my
touching.
sentence. So please let me see if I can understand what you're saying, and then I'll make my comment. And I see we have some other people already joining us. So today we're going to have just
Okay.
a general chat. And we're starting out with this blog that Abernathy has pointed out here. This is a conversation between himself and the host of the blog. And it's about the multiverse and the ether, and specifically the idea that that there is a many collection of galaxies, and they exist only inside this ether, and this ether doesn't exist outside of those galaxies, and that there shouldn't be say any light over there. So this is the speculation. So the first comment is saying that
Yes.
this kind of depends on our ability to how far we can see out. And so currently, cosmology has found things which would indicate a 13.8 billion year age of the universe. And that's when they speculate that the Big Bang happened. So there's this prediction here. Now, I'm not quite sure whose prediction this is, but the prediction
It is a
is
prediction of Dr. Glenn Burchard.
yeah. Well, once again, please try not to interrupt me while I'm trying to explain what I'm trying to say here. So the blog goes on to say there's a prediction that they will discover something older than 13.8 billion years. And I suppose this would be kind of embarrassing to the Big Bang theorist who said that, well, the universe is 13.8 billion years, but oops, we found something which is 20 billion years old. And then if they get a better telescope, they might say, oops, we found something that was 30 billion years old. And then as soon as far as they can look out, the universe will just get continually older, which would seem to be kind of embarrassing to the Big Bang Theory. But the James Webb Space Telescope isn't up yet. So let's take a look at the James Webb Space Telescope here. So the James Webb Space Telescope is basically supposed to be the replacement of the Hubble Space Telescope, but it doesn't look anything like the Hubble. And it actually doesn't
It's a more technical advance.
actually doesn't observe things in the visible spectrum, I don't think. So it will observe in the lower frequency range from a lower, longer wavelength visible light through mid-infrared. And this will allow the telescope to observe high redshift objects which are too old and too distant for the Hubble and other instruments to observe. And it has to be kept extremely cold, so it's got this gigantic reflector on the bottom of it to keep the instruments below 370 degrees Fahrenheit, which is really cold. That's like minus 220 Celsius. So when is this thing? This thing is scheduled to launch in March 2020.
The reason they're looking in the infrared is because as you go, according to the cosmological theory, the galaxies, the further away, are further redshifted, and since they're further redshifted, you can only see them in the infrared.
See, I have a question. If there is no light beyond 13.8 billion years, even this telescope will not be able to detect that. Because if there is no light beyond 13.8 billion light years, then the problem is that there will be no light over there. Even if any object exists over there.
Well, I think what's relevant to this conversation is the picture taken by the Hubble, which is called the Hubble Deep Field picture. And the goal there was to go and find the most empty spot in the sky as you possibly can, and then go and image that for like a long time so you can see whether there's really anything there.
Doesn't look any different than a close-up view of the universe.
Yeah, that was the funny thing.
That doesn't look any different than my view of a telescope picture of the Kuma galaxy cluster.
Yeah, exactly. That if the universe has an edge somewhere, we would think that things would get a little bit sparser, at least in some direction. But this Hubble Deep Field picture shows that every single speck you can see on this picture is actually a galaxy. Those aren't stars; those are galaxies of every single time going as far back as the Hubble can see, with really no sign of them, decreasing. So
yes.
So this picture kind of tells me that the universe extends very far back.
Actually, it is not expanding. It is a misconception we had till now. This expansion of the universe is based on Einstein's untired light theory, which is a false theory.
Well, I don't know that Einstein had anything to do with Big Bang Theory. Did he?
It has. Actually, you can contact Dr. Glenn Borchardt. Shall I give you the email address? He will tell you everything. He has a book also named Infinite Universe Theory. Shall I give you the email address of Dr. Glenn Borchardt?
Glenn Borchardt? Well, he's one of our more famous science dissidents.
Yes, he has proved that the Big Bang Theory is wrong. You know him?
Yeah. I mean, there's a lot of people who might think that the Big Bang Theory is wrong, although proving that is I don't know. How would you prove that?
Because see, the Andromeda galaxy, it is moving close to us. It is the only galaxy which is moving close to us. Other galaxies are moving far away from us. This proves that the Big Bang Theory is wrong, because if the Big Bang Theory is wrong, all the galaxies would move far away from each other, from one another. But if one galaxy is coming towards us, it means that the Big Bang Theory is wrong.
No, not necessarily. I mean, you could have two galaxies which are basically at the same distance but are going at different vector directions. So I could see that occasionally there would be some galaxies moving towards each other. So logically, I don't think that that in itself would falsify the expansion, because the expansion doesn't say that. I mean, if everything were absolutely evenly expanding, then yes, but I don't think that in a chaotic environment you could say that no two particles would ever be heading towards each other.
But this so-called age of the universe is got, I think, merely by extrapolating back. If you assume that the redshift is due to expansion, and you take Hubble's law to be that, and you just extrapolate back to time zero, you get this 13.8 thousand million years ago. Now, do you know, Franklin or anybody else, what they say is the maximum distance that they can see? I mean, it doesn't equal this 13.8 thousand million years. I take it that would be quite a coincidence.
And that depends on what you suppose the maximum brightness of a galaxy or a quasar can be, and I'm sure that that's merely a subject of opinion. And the other thing is, what do you think the extinction is? Which would be, how much dimming in addition to the inverse squared dimming of light is out there. And that's a matter of opinion. So basically, the whole thing is just a matter of opinion.
It certainly is a matter of opinion, Harry, yes. I'm just wondering what the mainstream claim. I mean, do they claim that they can see exactly the same number of light years away as the Earth is old? If they do, by the way, well, then you can say that they've seen twice that distance, because you see it in both directions. And unless we were the center of the Big Bang, well, then you'd see very much more. You'd see twice.
Well, Ian, the real issue here is you have to kind of figure out what's the double talk. Okay, what are their assumptions? And it used to be years ago that they had this problem that the oldest stars were older than the Big Bang. So what they did was they fudged the Hubble constant so that they agreed with each other. So you follow what I'm saying?
Yes, yes.
And recently they've made the Hubble, it was at 50, okay? And that was during the 60s and 70s. But recently they've increased it up towards 70. So now the oldest stars are younger than the Big Bang. So everything fits now. So the problem that you have is that you're it's a trust me situation. They are really basically guessing at all of these things that they're doing. In other words, they're just kind of, well, we think based on what we think, we know what we're doing. This is a conclusion that we come to, but they never say that. And essentially all these calibrations of the stars and the distance scale, that's all subject to opinion. And what they've tried to do is they measure the distance scale using different methods, different standard stars. They use supernova, and then they try to argue that they're all consistent and they all come together. But in doing that, they have to fudge some of their assumptions. Remember now, it's all based on assumptions. Okay.
And even having introduced all those assumptions and having sort of fiddled around with the parameters to make things fit, they after all that still find that there's a discrepancy between what they're calculating in distance and speed of recession. So of course, as we all know, they introduce acceleration and they introduce dark energy.
So you're talking about trying to reconcile that with the Big Bang theories that they're using. So in other words, essentially here's the problem. The problem is they're assuming, okay, let me start at the beginning. At the beginning is around 1900, they made these astronomers were using spectroscopy to study the composition of stars. And so spectroscopy had been, pretty, it had been developed to the point where they had a pretty reasonably decent technology. And around 1900, some of these astronomers started measuring the spectral lines of galaxies. Okay, they've been doing this pretty regularly for stars. And when they did that, they found out that the spectral lines were red shifted. And so they said, oh, these galaxies are moving away from us at these tremendous speeds. Okay. And the issue here is that conclusion has never really been changed. In other words, that relatively simplistic assumption that was made at the very beginning, 100 years ago, has never really been changed. They're still really using that assumption that, that galaxies are moving away from us at very high speeds because the spectral lines are shifted. That's the assumption that they're using. And that's pretty much, nobody's really, so we're kind of locked into that assumption being correct.
Yes.
I see, Jim, you have your flag raised. Go ahead. Jim, are you there?
Yes, I'm here.
Hear me? Can you hear me?
We can hear you. That's you, Jim.
Yeah,
Go ahead.
Eric Lerner published a paper that's called Observation of Contradict Galaxy Size and Surface Brightness Predictions that are based on an expanding universe hypothesis.
Yeah,
So
this has been done before. There's nothing, this is another one of their methods that they use to estimate.
No. He's saying that the universe, he's saying that the universe is not expanding. He's saying that his
well, like I said, it's all about opinion, and they really haven't changed their opinion since the first opinion that was put forward over 100 years ago. So that was the first opinion, and they've never really changed their opinion, although there's been a lot of argument about it. It's still the opinion that is the predominant opinion.
Well, Hubble himself believed in the tired light theory, that it's just the redshift is just a function of distance, it's not a velocity. But nobody's been able to come up with a mechanism for the tired light hypothesis, and I guess that's the main reason why it's been rejected.
Well, yeah, because they say, well, you didn't present a very convincing case that would change the majority opinion. So all you really have is a majority opinion. And the majority opinion is sort of buttressed by the fact that the textbooks all teach the majority opinion, and all of the scientists, when they speak in public, adhere to the majority opinion, and anybody who disagrees with the majority opinion is essentially, dismissed as a crackpot.
And they've graced this accepted opinion with the name of Hubble, because they say, oh, Hubble discovered that the universe is expanding. Whereas, as Jim basically said there, Hubble just said, look, I'm investigating a relationship between the distance of distant galaxies and nebulae and the redshift. Now, this may be due to tired light. It may be due to the Doppler effect. There are various causes. That's all Hubble said.
The Doppler effect is of two types, blue shift and red shift. When the galaxies are coming towards us, it is blue shift, and when they are moving away from us, it is red shift. So
when you get far enough away, everything's redshifted. nearby, there are some galaxies that are blue shifted.
I'm not getting you.
Michael, you've got your flag raised again.
Well, a few decades ago, they always thought that the universe was 26 billion years old on the basis of measurements of the decay rates of certain elements in distant stars. And that seemed like a pretty solid theory. I mean, the criteria were, decay rates of known elements. And then they changed it to 13 billion, half as much, on the basis of measurements of redshifts and recessional velocities, etc. Well, of course, I subscribe to an aether theory and creationist ideology of the universe, so I have quite a different opinion about the whole thing, and that we're not expanding the universe. We're approaching a second universe, which was created for re-energizing a tired universe, which is our universe. I mean, my whole outlook is different, but anyway, I still think that 26 billion has never been. I mean, we make assumptions about velocity of light through the space, which doesn't consider the possibility that an ether exists there, which is, it could affect the velocity of light. So there are a whole lot of variables here and a lot of assumptions going on that, well, I guess I'm a crackpot then, but I don't agree with a lot of it.
So, Mitch, you had a comment?
Thanks, Franklin. Yeah, Glenn Borchardt in his most recent book, the Infinite Universe Theory, he actually says that there's really, like you said, there's no way to really prove one way or the other who's right and who's wrong, because you can't really travel to the end of the universe. He does have, and he talks a lot about assumptions too. It all depends on your assumptions. And he actually wrote another book, The 10 Assumptions of Science, that where he lists 10 basic assumptions, and he says in order for a theory to really hold, it's got to hold up against all the assumptions, and they can't contradict each other. And he goes into lengths showing that his theories don't or coincide with all the 10 assumptions, and they don't contradict. And he talks about the tired light theory and a bunch of other ones. And he doesn't believe in the Big Bang either. That's one of his main points, is he's against the Big Bang. But he talks a lot about that in his most recent book, The Infinite Universe Theory.
So I've been sharing this answer on Yahoo about the age of the universe. So they say that another piece of data that supports the calculations is that the star HE15230901 is the oldest star that we know of, and is 13.2 billion years old. So this was determined by a method similar to carbon dating. The science measuring the light spectrum of the star determined how many radioactive elements it contained compared to other elements. Since radioactive elements decay over time and regular elements don't, the amount of radioactivity left can be used to calculate how long the star has been around for. So that gives you some idea. I think Harry mentioned this is a spectrographic method that they use. Give you some idea about how they measure the age of the oldest things in the universe.
And Glenn also touches on that also, and he says that every so many years they're readjusting the size of the universe, because they can see further and further out as technology gets better. And he says that they're always adjusting how big the universe is. So he says that kind of gives you a clue that they really don't know. They have no idea themselves, because we're still improving technology. We're able to see further and further.
Yeah, that was going back to the original post the blogs that we were looking at. So they're going to put up this James Webb Space Telescope in 2021, and they're probably going to find things that are older than 13.8 billion years.
Well, there's another. There's some people even call it a crisis. That there are two different methods of estimating the Hubble constant. One using the Planck satellite, and the other using the distance ladder, which was the original method of calculating the Hubble constant. So the 13.8 billion is based on the Hubble constant of 68. But the that's what Planck satellite calculations give you. But the distance ladder is now saying it's more like 73, which would make the universe, according to the universe's age, according to the Big Bang theory, only 12.8 billion years old, which would be less than some of the stars in our local galaxy in our oldest clusters. But they don't want to talk about that.
Well, basically, they don't really know for sure, but they're going to tell us that they do. That's the issue, in my opinion.
Well, I'm kind of wondering when they get the James Webb telescope up there, and they may in fact find out they can't actually determine an endpoint for the universe, that they're going to have to assign, the Big Bang to like 100 billion years or an infinite billion years. And,
well, they've got lots of room in their theories. I mean, currently we have this inflationary universe theory, which, is kind of a fudge factor applied to the traditional Big Bang theory. So, and then they have missing mass and dark energy and all these other fudge factors they can throw in. I doubt that they're going to let go of their assumptions, of their fundamental assumptions anytime soon. And the real issue is, can experiments prove anything or disprove your assumptions and show that they're false? And I don't really, that's really the issue. The issue is, can you show that the assumptions that scientists are using that they base their theories on are false? And it seems like that's not the case. What they do is they just modify the existing set of assumptions by adding more assumptions.
Yep, that would tend to be the history of science. But that's the question here. So they're going to get a significant new piece of information when the James Webb Space Telescope goes up. And a lot of these theories are going to be put to the test, because you will be able to see further.
What makes you think that they're really going to be put to the test?
Well, they are spending
I did not say.
dollars to put this thing up, so you'd hope we get some results. But you never know. So, Bill, you have a question?
I did not say that it will be test. He himself only said that it will be put to test.
Yes,
Bill, you want to comment?
Franklin. I don't think you all have talked about the current politically correct philosophies of science. You have, starting in the 1850s and 60s, you have the existential philosophy of science, which says you do not falsify any theory in science by logic. And so if you disprove a particular assumption, it makes no difference. You can't falsify a theory because it has a bunch of false assumptions. And then that was further improved, I guess you'd say, when they did the postmodern philosophy of science starting in the 1960s. So we've already have almost 60 years on the postmodern philosophy of science. And it says that if you discover something in chemistry, that's its own separate silo, and physics is another one. So if the chemist disproves theories that a physicist has, that doesn't count. Only what physicists do count in the physics silo, and the people who run the silo are physicists. And the chemistry has its own silo of chemistry, astronomy has its own silo, this is astronomers, and biology has its, and so we no longer have a university, we have a multiversity. And so anyway, we attempt from time to time to apply logic in our chats, but logic has no role in the current politically correct philosophy of science and the politically correct scientific method. And so, for instance, if general relativity theory cannot predict the gravity in our solar system or the gravity in spiral galaxies in the outer arms of spiral galaxies, they don't falsify the theory because experiment shows it doesn't agree with data. No, they just make a separate theory called dark matter and dark energy to supplement it. So we don't use logic at all in the modern science, and we don't use experiments, because if one experiment doesn't support our theory, well, we just invent another theory to supplement the theory. And that's how we do things.
All right. How are you doing?
By the way, the age of the Earth can be shown to be between 5 and 10 years.
I don't know when you can come and take a look at it.
Let's see here. If you're not speaking, please mute.
Okay, I've got one
We're getting
going.
some extra conversation going here. Cornelius, your flag is up.
Okay.
My
All right.
speaker working okay? My
Yes.
okay?
Go ahead, Cornelius.
All right, go ahead.
Louder now?
You're very quiet. We can barely hear you.
Yes.
I'm not going to
Yes.
speak if my voice is coming across clearly. I don't want to confuse things. I'm just going to let it go. I'm going to not speak.
Okay, if you have any comments, you can put them in the chat, and I can monitor those as well. Okay, but getting back to the original blog here. So we've been talking a little bit about the Big Bang. Now, if there was a Big Bang, then that would imply that there is an edge to the universe. And I think Average Technique's question is would there be anything beyond that edge? Because none of this really addresses his main concern, which is that he doesn't think that there's any ether existent on that outside edge if it existed, versus some other people who would think that if the ether exists infinitely and everywhere, so even if you did believe in the Big Bang, you would think that there would still be this ether substance existent beyond even the edge of the Big Bang. Of course, presuming that happened. Or on the other hand, I would say that my own personal opinion is that I wasn't there for the beginning of the universe, so I really can't say that there was a beginning. I prefer to think that the universe does have an infinite extent, and it looks the same no matter where we look at it, and that it's always been around. There's never been a beginning. There will never be an end, would be my personal opinion. But, I have nothing to back that up other than there are logical problems with it having a beginning, I would say. Although there is this whole question of what on earth do we mean, what is logical? I mean, you can say that, but it means really nothing. Because I would think that there are a lot of logical problems with like a lot of the theories that the dissidents have. So I just wanted to throw out the idea that what we mean by logic is that everything that we know about a particular question evaluates to be true. So an example of something would be not logical is for me to say this object is all white and this object is all black. So logic in this case would mean that both of those statements cannot evaluate true at the same time. So therefore that would mean a logical contradiction, meaning that both of those can't possibly evaluate the true at the same time. So hopefully if we're saying something is illogical, then we would be able to put up such statements saying this is one statement and this is another statement, those statements contradict each other, and therefore we say that something is not logical. So that's, one specific way to say what is logic, what is not logic. It's more a question of truth for all your known statements versus contradictions. So, Michael, you had a flag, and then Ian.
Well, I think logic has a lot to do with comprehensive coverage of all the facts, and not just explaining this and explaining that and separately. And in my model of the ether, you had a universal oscillation, then you had that transition to a universal vibrational ether, and then there were islands of quantum islands, quantally structured islands, which came about through the ether energies, which were highly aligned and entrained, and fluxing energies, which created foci of energy which are unimaginable in this ether macrocosm, which preceded our quantally structured universe. And that from these islands they sent out electrons, and if you send an electron into a virgin region of ether, it will quantize in a chain reactionally. So this all comes together. I mean, it explains everything, that kind of a model. And of course, there's no Big Bang in that, and then the empirical observation of quantum mechanics doesn't fit into it, but it explains more than the empirical and Big Bang theories do.
Yes.
Such as?
Well, the beginning,
Yes.
it has a beginning, it has a logical progression to quantum. In other words, if you had an ether macrocosm with an entity who could project electrons into a virgin region of the ether, then that would create quantization chain reactionally, and then it would all fit together, because an ether macrocosm would have been unstable magnetically. You would have had magnetic transients and instability, and you had to create a quantally structured universe to provide the stability, magnetic stability, for a kind of world that we live in now, which is structured. And, it all makes sense. I mean, it's just, to me, it's more logical because it's so comprehensive, that kind of a model. Of course, it's creationist, and creationism has a lot of opponents too. So you run into opposition no matter where you go. But if you put everything together, that's what I'm saying.
Well, I think this falls into the category of self-consistent theories, which is, if you that there is a progression, and the knee bone's connected to the ankle bone and such. And to a large extent, see, none of these things can be falsifiable, because it starts from starting assumptions and then goes outward. But that kind of makes it difficult to determine whether your theory is actually right or wrong. And I suppose that's where the experiments come into play, where the arbiter of
there's no experiments that you can apply to the problem of cosmology. What are you going to do? Experiment by creating universes?
Yeah, that would be a big problem with cosmology, in that we generally are stuck with what we can observe. We can't go create a star or something. Although maybe we can do that, maybe a little bit in our accelerators or something. Literally, we create what we think are black holes or whatnot. So I wouldn't say that.
As I said before, okay, the basic bottom line is you have science, and I think Bill made the case pretty well. But the reality is that astronomers basically measured the velocity of stars with spectrographs by measuring the spectral lines, and they were able to measure the velocities by showing how they were shifted. And when they measured galaxies, they found the galaxies were shifted far more than they were able to comprehend. And if you read any of the books from around 1900, they talk about the fastest galaxy known receding from the Earth. And, that assumption, that's an empirical fact according to their thought process. Their thought process is, okay, I measure the spectral lines are shifted to the red relative to the spectral lines on the Earth. That is a velocity because that's how I've always interpreted that spectral shift. And so therefore these galaxies are receding at these high velocities from us. And that is an interpretation of an empirical fact. They've never questioned that empirical interpretation.
Is my mic working any better now?
Yes, we can hear you better. That's you, Cornelius?
So do you understand what I'm saying, Franklin?
Well, I mean, that's the general philosophy of science that we've been talking about.
The bottom line is anybody who proposes a theory to say, okay, this redshift is not caused by a velocity and it's caused by something else has a burden of proof that really can't be satisfied because there's nothing that you can produce that can actually disprove that thesis.
Well, one thing I was thinking about is in our communications with our deep space probes, like the Voyagers, we're apparently still in communications with those. I would think that if there is a tired light effect, that we might be able to directly measure that from those probes, since we think we have an idea exactly where they are. We think we have an idea of exactly how fast they're going, and we know what frequency they're being transmitted at. So if there is no tired light, then we should be able to recover that signal with perfect fidelity. But if there is a tired light, then someone should be able to make a prediction saying that it's going to become redshifted by X amount. And although I think what the true experimental result is that it's blue shifted from what they expect. So that is not exactly helping tired light's case. But I'm just saying that the possibility that we could directly measure a tired light effect if we were looking for it.
One of the largest redshifts is due to what we call the gravitational redshift. We've proved that it exists in experiments then at Princeton University, and but they never take it into account. Astronomers ignore it.
Yeah, we have a gravitational redshift, and some people think that shift just accumulates as it passes through all the gravity fields. So, although I'm not sure whether that would be the case, because I would think that if there's a shift, then it would be a shift forward and a shift backward as it goes, approaches and recedes, and it might all just wash out. I don't know. I haven't looked into it that much. But Ian, you have your flag up?
Yes, thank you, Franklin. A couple of things. First, getting back to the discussion on logic. Now, I would submit that we need to be very careful when ostensibly using logic, basically because we're not perfectly logical machines, and furthermore, we're not omniscient. So you can possibly try to prove anything by logic. Now, for example, the question as to whether the Earth is infinite in space and time or finite in space and time. Now, Kant, in his Critique of Pure Reason, has these antinomies, which are like opposites, and he proves actually by logic that the Earth is that the universe is infinite in space and time, and then he has on the other side the antimony, which is the contrary. So basically, there's flawed logic here. Now, I personally subscribe to your prejudice. I think it's my prejudice as well. I work on the basis that the universe is infinite in space and time. But I do concede there are some logical difficulties which could be raised there. Now, Bill, of course, raised this business about modern science, and that's correct. But you see, I think that the mainstream people don't willingly say that they're not logical and they're happy to abandon logic. They claim to use logic, and that's why when they see some apparent contradiction, in the results of experiment from what they predicted. They don't say, well, you better just suck it and see. They say we better introduce this fudge factor. So that's where all the dark energy and the dark matter and the Hubble's constant. Now, the Hubble's constant, it's true, as Harry said earlier, that it has been fudged around, to try to get a better fit. But there's been quite a variation in their experimental results when they try to relate the distance of distant celestial objects with the redshift, and they got sort of figures of anything from 50 to 100. Now, I would claim that actually throws great doubt on the linear law. Forget about velocity of recession, forget about expanding universe. The so-called linear relationship between distance and redshift. Now, you know that I've looked at this, and I've actually formulated an exponential law. I basically accept the tired light principle and the dissipation, and I accept an exponential law. So it's only at a very small part of the curve will you get an approximate linear relationship. And when you go further out, you'll get quite different values of the Hubble constant if you're trying to fit it to a linear curve. So that's another problem. Yes, I think that's all I wanted to say for the moment. Thank you, Franklin.
Yeah, I think maybe the Webb telescope might be able to, either confirm or deny this nonlinear relationship.
Well, I do concede that, and yes, you were saying that earlier. You were saying that you could do some sort of experiments. You see, I would maintain that even the existing data we have fit very poorly to a linear law. It's quite complex. You have to vary the parameters, the Hubble constant, and then you get very, very enormous postulated luminosity of very distant galaxies and very, very high recession speeds, almost approaching the speed of light. Whereas if you adopt a sort of an exponential curve, you don't need to fiddle around with these figures, and it seems to fit much more neatly. So I would claim that the initial results we have from the experiments that we have so far does seem to throw grave doubt upon the linear relationship between redshift and distance. And I do agree with you that perhaps, hopefully indeed, with the further results coming from the James Webb telescope, we'll be able to enhance the experimental information in this regard.
Okay. So Cornelius, you have raised your flag?
Is my mic working better now?
Yeah, we can hear you.
Yes.
Okay. I don't have so much a theory here as a kind of an analogy, an alternate analogy. Bill mentioned, that Hubble just said that there was a redshift, and he didn't claim for talk about the expansion of the universe or anything. The analogy I have is basically related to tension within a carrier media. If you look at take as an example, like a spherical surface, like a drum surface, a drum head, and you tension the drum head, just because of the physical nature of the drum head, the tension that you put on the outer perimeter of that will be concentrated and will be more tense towards the center because all the tension is pulling towards the center of that drum head. If you were to beat that drum head or tap that drum head in any particular location, you'll get a different frequency on that drum head for the same tap intensity, same energy intensity you put into it, depending on where you put it. The center being the most tense will vibrate faster than the outside edge of that drum head. And consequently also, if you were to tension that drum head while it's vibrating, the vibration speed will not increase, the frequency won't increase, but the waves will travel faster and become lengthened. So in both cases, what you've got is you aren't really changing the diameter of it, you're changing the tension within it. You might, in reality, in order to change the tension, you will have to very, very slightly change the diameter of the drum head in order to change the tension greatly because of strictly because of the material characteristic of the drumhead. But I propose that, because of that, if you look at that as an analogy, any physical, any process happening within the center of the drumhead, if the same energy is put into a process in the outside edge of the drumhead, in other words, the center of the universe versus towards the edge, and even if there's an infinite universe, there is the possibility that there's inconsistencies in the degree of tension within regions of that universe. And because of that, the same process will happen at a different rate in a lower tension area, giving the appearance of a redshift for that process. So that star would look like red because it's in a different tension area. And you can also have the same type of thing if you were to start a vibration and the vibration were to move linearly across that surface. Then if it's moving away from you as it's vibrating, then you're going to get redshift also, because the waves coming back towards you will be also moving, the source of those waves will be moving away from you, which we know is the Doppler shift. So the one simulates more the gravitational redshift that Bill is saying that was often ignored, and the one is the normal Doppler redshift we're indicating of. But in all these cases, you're not really changing the diameter or the size of the media. You're just changing the tension within the media to give you these various redshift characteristics. That's kind of an analogy that I perceive it as, and it's much more dynamic than this, but that's a fundamental concept.
Okay, so you're coming up with some alternate explanation for the redshift other than expansion.
Correct.
Okay. Yeah, you seem to be going off way far away just to come up with that explanation. Okay, but I think we understand.
I don't think that's so far away. I mean, it's reality. If you look at even a tension surface, that's the way the tension surface works. So I don't know how far away you consider that to be. It depends on your viewpoint. But to me, it's a very simplistic explanation for a redshift and many other things related to that. But that's just the fundamental part that explains the redshift part.
Well, the part that I wouldn't get is that I know that when you stretch a drum, that the tension is in fact completely even everywhere across the drum. That's a basic property of it, and therefore everything that's happening on that drum would logically occur at the same rate, and then that would not lead to anything that looks like redshift to me. That would be my thinking there.
Well, I think you need to put a stress meter within your drum surface and verify that, and I think you'll find that that's not correct.
No, I think that's totally, at least for drums, the tension has to be pretty even, or at least that's what you attempt to do. I suppose if you made it really, you just tightened only one side of the drum and let everything go slack, and then let there be start to get like waves and folds in there, that you have different kind of tensions, but that's generally not the what you're trying to obtain with the drum head. You're trying to as
geometry itself would dictate differently, but if you just do vector summations of the tension from, if you have a 10 people standing outside diameter of a surface of a diaphragm, and you have them pull, each one of them will pull a little bit, but the tension in the middle will be the summation of all those tensions. And so
well, it would be.
So logically, there will be more tension in the center.
Let's get back to Aberchecky's blog here. So presuming that, let's see here, his second point here he's making is that he claims that he can prove that the ether doesn't exist everywhere, since this is his main claim, by looking at black holes. So, and it says his claim here is that nothing, not even electromagnetic radiation such as light, can escape from inside it. And actually, I think this claim is wrong, and that he believes that there's no light, because there is no ether over in the black hole. So particles which go there cannot be seen anymore because there's no light over there. So there are actually no such things as black holes in the universe. Since particles which go over there cannot be seen anymore, mainstream physics has assumed that the region is a black hole from where particles cannot escape. The region is only a place in the universe where the ether does not exist. So that is the contention here. The response from the blog host is that that no one's really seen a black hole. So it's not like they put a telescope on it saying, oh, there's no light there. And his opinion is that they appear to be a product of mathematical imagination. And he's saying that even Hawking said that they're really gray holes. And his interpretation is that the only evidence we have for a galactic nucleus, where we see where there's at vortice and the center contains a great mass and soon to be black holes, but without the blackness, because obviously it seems very bright in the middle of the galaxy. And so he thinks that the lack of ether hypothesis is unnecessary.
That I agree with. Now I agree with that. But even if black hole may contain ether, but still beyond 13.8 light years, if we really cannot see anything, it would mean that there is really no ether over there. But still, some objects can still exist over there, even if those objects exist, and if there is no light, we will never be able to see those objects, because without light we cannot see anything.
Well, I would say that, it's true that if you're an etherist and you find a region that doesn't have ether on it, that it should be completely opaque to light. Light should not be able to travel through it. So I would totally agree with that. So if I were to create like a 1 cubic foot area in front of me that was void of ether, then I'm not exactly sure what it would look like. It would probably look like a mirror. Probably because it would have to exclude all light attempting to enter it. So the only way I could do that is by reflecting it. So I would see this silver 1 foot cubic, 1 foot cube floating in front of my face, where there is an exclusion of ether. At least that would be kind of my guess. If you could produce a region that is completely devoid of ether. So I'm thinking you'd be seeing a disco ball and not something black. It has to be something with the light that's impinging upon it. So that would be a completely different way of thinking about it. But his response, I think, is fairly skeptical of the existence of black holes here at all. And he doesn't really address the mechanism by which black holes get their blackness from. Mainstream.
This to me, this is just a scientific speculation of black holes. How can you prove that it exists? All you can do is you can make a theory, and then you look out in space and see if you can find something that looks like it might resemble what your theory predicts. And that's all they've done. But the reality is that what they're calling black holes really don't seem to be black holes at all. They're just, what do you think a black hole is? And so because a black hole is an ill-defined theoretical concept, that allows them to go out and find things that they observe, and now they're calling everything that they can conceive of as being a black hole, as if they really know that it's a black hole when they don't. Okay? That's the problem. The problem is they're making statements as if they're true when they don't know whether they're true or not.
Yeah, so my question is, if you're trying to disprove or prove something using the concept of a black hole, then, how reliable is just the assumption, first of all, that there is a black hole? to average me, it's like, I'm not sure that you can prove that your claim is correct by using black holes when the existence of black holes themselves, I think, would be very much in question.
Let's just take this for what it really is. I'm a scientist and I'm an expert and I have a PhD and I say it's so because I say so. And you're saying that that's not true. And so I can just say you're wrong because I'm an expert and you're not. That's basically most of what all these arguments are about. Do you understand what I'm saying?
So, good thing we don't have any experts around here.
The problem is these experts are claiming things are so when their proof is really not very convincing at all. Okay, and they don't allow alternative theories to be considered, and the funding, because there's a competition for funding, the government is giving these academic people who claim that they know what they're talking about the money to prove their theories, and they're not giving money to people who aren't these academics to prove their theories. So what theories do you think are going to be proved and accepted? The theories that are promoted by the so-called experts who have convinced the government to give them money. Okay? Am I not correct in this?
I think that's the way science works. Science chases the money.
Right. Now, the problem is that if I'm an expert and somebody comes along with an alternative theory, why should I allow that guy to get money that I should be getting? So I'm going to say that guy's wrong, right? Because he can't be right. I'm right. Give me the money. All right? The problem is that we have a science community, an ethic of science that says there can only be one right theory, there can only be one right scientific philosophy, and that philosophy is the philosophy that I have and all my friends have. And I'm going to disallow anybody else from expressing his ideas and writing books, because we don't want anybody to write books that contradict our truth of the world. And that's basically what they're doing. It's not really science. It's only nothing more than the opinion of the politically correct, put in a more modern view of it, which is what Phil Lucas is saying in a different way.
Well, there are a lot of people claiming a lot of awfully far out stuff, like Lisa Randall, very famous physicist at Harvard University.
Are they getting any funding from NASA?
Oh, I'm sure she's getting funding from something. She's got very many popular books all about, the speculation that there are multiverses and that gravity is bleeding in from these multiverses, and that's why it's so weak. And that's all. This seems to be just as wildly speculative as the same stuff that us dissidents come up with, right?
Well, there you have a problem. Okay, but the bottom line is, the first thing that you come to, I'm an amateur astronomer. The first thing I run into when I read anything about cosmology or any of this stuff is I want to look out in my telescope, or my telescope's not powerful enough to really do anything, but there's billions of pictures, thousands and thousands of pictures on the internet of galaxies. And you can look at these pictures of galaxies and you can think to yourself, okay, how is this explained by the current scientific theory of the Big Bang Theory? And it doesn't make any sense. When you read what they try to tell you about how galaxies are formed and how stars formed, it makes no sense. Okay? I can't see how any of those theories are true. All right? Now, the problem is they don't allow any discussion of alternative theories because they only allow one theory, and the only theory they allow is their theory. That's the problem with science.
Or it could just be sour grapes at our point, right?
No, no. So the real issue is we can sit here and talk all day about all these wonderful theories, but the bottom line is nobody's paying attention, and nobody in the scientific establishment gives a darn. And they're just going to dismiss anything that you say because everything you say has to be wrong because they say so. So if in this case of this blog, if you go on there into these scientific discussion things and you suggest that maybe currently what we believe is wrong, and that really, and they just dump all over you. They cannot tolerate the thought that what they believe might be incorrect because they've assumed all their assumptions are correct. They assume all the facts that they think that they believe in are correct because they believe in all of the interpretations, all the observations, the experiments that are told to them in the textbooks as they've been beaten into their heads that this is what the truth is, and science knows what the truth is, and science can establish what is true and reject what is false, and they can't do any of those things. It's all just fake. It's a philosophy that isn't really doing what it's claiming. They have no idea what the universe is. They have no idea whether the Big Bang Theory is true or not. It's completely illogical to assume that it's true. We're just little human beings, and our intellects aren't big enough to comprehend what the universe is. And yet they're telling us they know the answer. It's absurd.
Well, the hypocrisy, which is quite galling. I think many of the things you talk about there, Harry, are symptomatic of the human condition. And certainly if we look back into history, we find, totalitarianism with regard to thought in politics, in religion, in history, you name it, any human endeavor, there has been an orthodoxy. And there is today, of course, in what is considered correct, politically correct, if you like, in all spheres of activity. But here we're meant to have a science which is exact. It's based on mathematics, which is quantitative, and it's based on evidence. It's based on repeatable experiments, and it's based upon logic. So I know it's not based on logic, but so they claim it's based on logic, and yet you find the result is quite the opposite. It's the same as the worst examples of totalitarianism in human endeavor, where, as you say, Harry, this is right because I say so, and I'm qualified, and I'm part of the establishment. And I'm wondering why this has taken a hold so much on, say, astronomy and the physical sciences concerned with the universe. I take the discussion points that it's a question of preserving one's funding and one's status in society and one's income and all that sort of thing, and persuading the government and powerful interests to support you. But I suspect maybe it's because so little is known and so little can be known of the distant regions of the universe that this is therefore ripe for these operatives to indulge themselves in this particular area and introduce an orthodoxy which cannot be questioned. That's anyway my provisional explanation for all this, which seems otherwise
right. Well, I guess my point is, and
paradoxical.
This is what I've been trying to say, and I agree with you, Ian. What I've been trying to say is that if you put forth a theory, okay, and if you're not, if you don't have a sponsor, like, in the old days, the scientists had noblemen who sponsored their scientific research, but you sort of need a sponsor. You need somebody with credibility, and the credibility now flows from government. So the bottom line is, without that credibility behind your theory, you can have, a tremendously great theory and lots of believers, maybe 100 or so, but nobody's going to really pay attention.
So, Harry, do you think black holes exist? What's your opinion on that?
That's like asking me, do ghosts exist? If
Yeah,
you're
after my conversation
spirits,
with Glenn Burchard, I came to know that black hole, but the hole is not actually because of lack of ether. It is actually a gray hole. I agree with him after having the conversation.
I didn't quite understand that. I don't think that's a legitimate question, Franklin, is my point. There's no, it's just an imaginary concept. That's all it is.
Yes.
Well, I think your response is interesting. Like, do ghosts exist? And see, so I personally have never seen a ghost, but I've seen lots of TV programs and eyewitness accounts that suggest that these things do exist. But personally, I have no firsthand evidence for their existence. So is it kind of like that for you?
I mean, I could say I'm an astronomer and I could say, oh, we know black holes exist because, and I can cite, and I can cite all these papers and I can cite all these catalog numbers of all these objects that they claim are black holes. But when you really get down to it, it's all just interpretation of data. Well, I'm interpreting this data to be that that's a black hole. That's all they're doing. That doesn't prove that they exist. It's just an interpretation of an imaginary concept and saying this imaginary concept exists out there because I've created this interpretation that seems plausible. That's all they're doing.
Harry, being an amateur astronomer or not, what do you think of where they say they've seen or where you've seen images of the like the Einstein rings or the basically the gravitational lens?
Yeah, that's another
multiple images of the stars from different angles.
Well, when you look at those pictures, you don't see a ring. You see a bunch. I mean, I'm sorry. That's just. Yeah, they're just stretching the interpretation of what they've seen.
Okay, what do you think about the basically when you see the gravitational lensing effect, where they see images of the same star groupings, in different.
It's all based on their interpretation.
Well,
it's all based on their interpretation.
But how do you interpret that when you see those images?
I don't have to interpret it. All I have to do is accept or not accept what they say. And, if I look at it and I don't think it's convincing, I don't think it's convincing.
Well, so I'm just showing you an actual telescope image of one of the so-called Einstein rings. So, Harry, what do you think's going on there?
I have no idea because I don't know how they did that picture.
It's a straight picture, visible light.
I don't know what it is. Could be lots of things.
But it also has no justification in being called an Einstein ring, I would maintain, unless it can be established that the deflection of the light is exactly as predicted by Einstein. I mean, you might as well call it a Newtonian ring or a classical physics ring, because in classical physics, Newton predicted a deflection of light near a gravitational body. It's actually half the value of Einstein's, but I think it's sort of like quite jazzy calling it an Einstein ring.
Well, I agree with you there.
I think that's only done popularly.
You don't want to use the word Einstein in this group. I understand that, but and basically that's why I tried to use the second term, which is gravitational lensing, which is probably much more accepted.
Yeah, that's the caption of this picture. It's a gravitationally just.
I see here that it's not a ring. It's a loop.
Well, you also understand that you have to have the object exactly in the center in order to get a perfect ring. I mean, they'll explain that to you.
Well, but their theory falls apart right there because they're telling me that they have a theory and then they present some evidence, and the evidence doesn't show the ring that they claim that ought to be produced. But because they have incomplete evidence, they say, okay, well, excuse us, our evidence is incomplete.
Well, Harry, if you're looking at a lens and you tilt that lens so it's not vertical, so you're not exactly in line with the focal
You're making an excuse that the
length of that.
prediction didn't come out as predicted.
No, I'm just saying you're not exactly at the focal point of that lens, so then you're not going to see the true, perfectly circular image.
Well, there's no ring here. Where's the ring? I don't see a ring.
And didn't I just explained to you why you don't see it? You're not at
Yeah, but
the
that's
focal
not
point.
that's not proof of anything. That doesn't prove that there's an Einstein ring. That's just an excuse for why it's not an Einstein ring.
Yeah.
Give me proof. Give me proof. See, this is the problem. The problem is you can always explain away discrepancies if your theory doesn't give you the exact result you want.
Yes, but the discrepancy was logically explained away. And
so what?
Unless you want to throw out logic, which you would claim modern science.
Well, that was your use of logic. I used it in an opposite way.
You just did what modern science has done, thrown out logic, because logic said this is why it isn't perfectly spherical.
What was your logic? I don't know why you want me to believe. I don't necessarily believe or disbelieve in Einstein rings. All I see is that's not a ring.
Well, what do you mean by that's not a ring? That's totally a ring.
It's not a ring. It's missing a whole part of it.
It's a partial ring. I have no argument. It's not a ring.
But even if it's a partial ring, that's still pretty incredible, right? Who cares if it's not a total ring? I mean, actually, if you look at it carefully, it is continuous. It is actually, when I'm looking at this, it's very dim, but it is continuous.
Well, I don't know. I mean, I'd have, you're giving me, you're essentially what it boils down to is the guy says, okay, here I found something. This is what it is, and he makes this big complicated argument. He writes all these papers and writes all this stuff, has all this blah, blah, blah. And you're supposed to believe him because of that. Well,
Harry, I can't believe
time to go through and check everything.
I can't believe you haven't made the point yet, Harry. That
what point is that?
What we were doing is talking about black holes, and the image we're looking at is a very bright, huge star in the middle to indicate gravitational lensing.
I don't really know what that proves. Yeah. Do you know that that's a star in the middle? Looks like a galaxy to me. It looks like a galaxy to me.
It proves that you haven't made the observation that this is not indication of a black hole. It's an indication of gravitational lensing around a very bright mass. So your observational skills are so concentrated on the fact that it's not a bright ring, it's not a perfect ring.
You asked me about Einstein rings.
Okay.
Well, I mean, this is just an observation. This is an empirical piece of evidence. No manipulation has been done with this photograph. How
do you know that? How do you know that? How do you know there was no manipulation?
Well, I presume that there was none. That is an assumption on my part.
So there's an assumption on your part.
I have seen multiple photos of this. They appear to be visible light photographs, unretouched. So, as far as
I don't know. I mean,
it's not because they retouched.
This is not an area where I have any real expertise, so I'm just going to say I'm skeptical. So there.
But I say, what's the big deal? I mean, what are they trying to establish here? Gravitational lensing is a classical phenomenon. What's this paper trying to do?
I think what they're trying to establish is that we see the same type of ring or the gravitational lensing effect. And they've seen images, they've got images where in the center of this gravitational lensing is not the bright star, but rather a black void, which seems to indicate that there's a mass there that caused the gravitational lensing, but the mass does not allow light, does not emit light, and does not allow light from behind it to be passed through. And I think this is kind of a precursor to the fact that they have other additional images where you don't have a perfect ring, but what you have is a star pattern that clearly looks like it's a reflection around a circle, or imaging itself around a circle in several different directions, indicating gravitational lensing around a mass that's not visible. And that's the next step. That's not the image that Franklin found, but there are some images that show that. And that's more like what I'm speaking of, is that in the center of this, there must be gravitation, is what they're explaining, a gravitational object, a massive object, and it's not visible. That non-visibility seems to indicate what they would consider a black hole. So
well, I'm also agnostic in regard to the question of black holes. I mean, there are certain phenomena there, all right, but they're trying to attribute an existence of some object with definite properties as the cause of those phenomena. Well, I doubt that. For example, I conceive that you would only get light from a distant object if you're the same distance away in light years as the time previous to the present time that it emitted the light. So, for example, if you were further away, the light wouldn't have reached you yet. If you were nearer, the light would have gone past you. So it is quite possible that bright objects could be the cause of the gravitational pull, but you're seeing a black object because you're not the right distance away, in time for the light to have come out. So there are various other explanations you can give.
I agree. There are other possible explanations for it, certainly.
Well, I think that, these photographs do provide some very strong evidence that light is bent by gravity. I would say that, and that the gravity can act like a lens. So I'm fairly convinced of that. Now, what this has to do with black holes is whether some astronomical object can have so much gravity that it will cause the light to bend down upon itself, which is something I am highly skeptical of, because I feel that gravitational lensing works like a lens, and that a lens can bend direction of a light ray as it heads through the lens, but it can't bend it like 180 and 360 degrees back out towards where it came from or anything like that. I mean, there's definitely a limit to how much the light can be bent. So to say that gravity can bend light, it's shown like in some animations like a fire hose where it goes out and actually goes back down. I don't think that's possible. I don't think any kind of lens can bend light that much. So I don't think that a black hole would be black, really. I don't.
Let's look at the simple atom, for instance. If you just look at a single light ray, a light emitted by an atom, absorbed by an atom. If a single light photon, a photon of light, whether you consider it a particle or whether you consider it a bump wave, gets absorbed by an atom and stays there, doesn't come back out. So isn't the atom essentially a black hole to that particular photon?
No, I don't think so. That would be a case of absorption, but light is absorbed by a black piece of paper, and I don't think we would call that a black hole. I think the point that mainstream is trying to make is that you've got gravity that's so strong that a passing light wave will get sucked into it, and that's the thing that I am highly doubtful of. Now we know that
the same thing. Wouldn't that be kind of like the same thing as a satellite passing too near something that's massive and getting sucked into its gravitational field?
That would be a closer analogy, yes.
Well, if you believe light can be bent by gravity and the satellite is also bent, direction is also bent by gravity, then both are possible logically.
Well, I'm saying let's slow down here a bit. When you're saying light is bent by gravity, that's not what mainstream is saying. Mainstream says that space-time is bent by the gravitational potential. Light is bent. Space and time is bent.
Agreed. It's a matter of way.
Okay, so now you have another question is, okay, that's one interpretation. You might have another interpretation that it's the path of light is bent because the speed of light changes as it passes near a galaxy. Okay, that's a different interpretation. of the same thing.
That's great. And either one of them can result in light being curved towards the center of a focal point, in which case it gets curved strong enough that it can't get out of its that focal point.
Right.
So
But
there is
here
a
I want to
potential.
point out that this simulation doesn't look like any of the pictures.
Oh, I don't know about the simulation. I mean, that's just something that.
I mean, here's the simulation. That simulation doesn't look like any of the pictures he showed. So right there you have, you know, I'm sorry, you know, to me, this sort of thing is nice to speculate about, but I mean, whether I'm convinced or not is, you know.
Yeah, well, this is totally simulation, although the ring is so formed right there where you can see it. There's a circular thing as it passes by that galaxy there, theoretically. So, but that's the thing that they're saying is similar to what we've been
Well, what
looking
I
at.
see in those pictures that you showed, like in this picture right here, what I see is a galaxy in the process of forming. And there are lots of galaxies that we know of, and you showed some other pictures earlier where you have a core like this, which is an orange core, and there are spiral arms around it. So this looks to me like it's a galaxy that's trying to form spiral arms.
Looks to me like it's a star that's previously exploded, and there's a bright light in the middle of it, collapsing.
Well, there's a different interpretation, right?
Exactly, Harry.
Yeah, and I guess it would be up to someone trying to say that this is a distorted image to piece together what the original galaxy looked like behind it. They're saying that this galaxy is actually behind that other galaxy.
Well, it doesn't look to me like that's the case because it's not a symmetrical ring. It would seem to me that it should be symmetrical, and it doesn't look.
No, I don't see any reason why it would need to be symmetrical. I mean, depending on where it's centered, lens is centered on the galaxy.
Now you're using the excuse that it doesn't have to be.
No, it absolutely doesn't have to be. In fact, it'd be really coincidental if it was.
The excuse that it doesn't have to be can, you know, I mean, so that's
in most cases it wouldn't be. So
you're saying my interpretation of the picture is wrong because you have a doesn't have to be interpretation.
Yes, it absolutely doesn't have to be. I mean, that is this close is remarkable.
And in essence, all of science basically boils down to opinion.
Absolutely, it is all opinion. So that's what we're talking about here.
Well, just opinion. Your opinion versus my opinion, and so why should your opinion be superior to my opinion?
Well, that would be the convincing, how convincing your arguments could possibly be, just like a jury of your peers.
You think that's so convincing? Convincing to who?
To a jury of your peers.
So people who don't know anything about astronomy would be entitled to cast judgment?
Absolutely. That would be us.
Yeah, right.
I'm not really interested in passing judgment myself.
We're the peanut gallery here.
Studying content.
Well, he brought up the word jury, so.
Okay, yeah. Well, I think it's just, I like an open discussion. I'm not saying to anyone, that's why I said I threw out these analogies, and they're just simply that, analogies, alternate explanations for, redshifting, just for discussion purposes.
Here's the thing, all right? I mean, I didn't even bring this up yet. The whole theory of the redshift is based on the assumption that the laws of physics are such that the spectral lines in atoms, okay, are always the same no matter where in the universe you are. Now that's an assumption, isn't it?
It sure is. Because we can't go to the other side of the universe, go measure the spectral frequency and confirm that it is in fact the same as what happens on Earth.
Well, so what you have is you have, a number of different assumptions that could be questioned. The fact is they don't really consider the assumption that the spectral lines could be different in different places in the universe as a permitted assumption because science depends on the fact that something has to be invariant when you make an observation or a conclusion. So the assumption is the spectral lines in these distant galaxies have to be the same as the spectral lines that are measured on the Earth if you're measured at that galaxy. Okay, now that's an assumption.
But that would seem to be a reasonable assumption.
Exactly,
but
it's reasonable.
Reasonable or not, it's still unproven.
Well, unless you get to the other galaxy, you're not going to prove it.
Correct. So
But
there's
even if you get to the other galaxy, what it's saying is that if you were in that galaxy's region of space, then based on all the equipment and your instrumentation, everything would change to the surrounding environment, and so your rulers would become shorter, your lights would move different speeds, but relative to the ruler that you brought with me and you and the clock you brought with you, everything, all the tools you brought with you to that galaxy, that experiment is going to have the same results, and that's what basically the conclusion that they've come to so far, which seems perfectly logical. If you go to the vibrational drumhead situation, the same amount of energy put into a tense surface versus a relaxed surface is going to give you a different wavelength if you look at it from the perspective of the tense surface. But if you look at it from the perspective of being in the same environment, then everything you're using is going to be, so one experiment relative to the results of another experiment are going to be the same. But if you do the experiment outside that environment, then it's going to look different.
It could be. So, Jim, you have raised your flag? Go ahead, Jim. Jim, your mic is open. Did you have a question? No? Well then, okay. Michael, you raise your flag.
Well, if I could be permitted another dissonant opinion about black holes, I subscribe to this creationist view, and one of the questions about the universe is what happened to all the antimatter. Well, if you have a creationist model, the creator would have had to channel the antimatter away from the brand new quantum universe as it was being created from the ether, and he would have used like unit channels in the ether to direct the antimatter towards the target area, which would be a black hole. And this isn't just my opinion. I've also seen it by other people who have dissonant views, like Rosicrucians, Theosophists, and people who claim to have occult knowledge of cosmic matters. I've also given that idea that black holes are actually antimatter, creational antimatter foci.
All right, so Jim, he has a comment that gravitational lensing doesn't need general relativity. So, I mean, that was brought up by Ian, in that even Newtonian mechanics predicts some gravitational lensing.
Yeah, can you hear me now?
We can hear you now.
Cool. Yeah, if you assume that there is an ether and that it has a variable density that's a function of the gravitational potential, and that density, the more dense the ether, the slower light travels, then you can explain gravitational lensing that way, as shown by Howard Hayden.
Yeah, that's how I think it works. That the gravitational ether is just due to a change in the refractive index of space around a gravitational object. So, as an etherist, I think that literally the ether is more concentrated down on the surface of the Earth, and therefore a light wave travels slower through that denser medium, and that's what causes the bending. But this is where I think that no matter how dense the object you have, it's not going to cause an incoming light wave to just fall into it. Versus, say, a satellite, as mentioned, a satellite can come to the Earth and fall into the Earth, but a light ray being slowed down by a denser medium is never going to actually change direction and fall down towards the Earth. So it's just a change in speed that between a faster, whenever you have something, a light wave traveling through a faster medium to a slower medium, it will switch directions, and it won't crash into the Earth like a satellite. So that's why I'm saying that, if you did have a black hole, it would not suck up all the light that's around it. It would just reflect the light around it, like we're seeing with these gravitational lensing type rings. So black hole, I guess if you could really see one, you would just see it as this thing that's got, you can see behind it with all these rings and stuff. It wouldn't actually be black, although that's still kind of a here nor there argument. I would say that the most interesting evidence of black hole that I've seen is that they have imaged all the stars orbiting around the core of the Milky Way galaxy, and they can see that there's something incredibly massive at the center that all of these stars appear to be looping around, but yet we don't actually see anything in the middle. So whatever that thing is, it's got a lot of mass, and it's not luminous, because we can see all the stars.
Back in the old days, they used to call these things supermassive objects, and they didn't call them black holes. And they changed the terminology from supermassive object to black hole. And so all they really did was change the name.
Yeah, I think so. I mean, instead of there being this mysterious black hole thing, there could just be something like the Earth, except like 1 billion times bigger, right? It's just a gigantic.
Why not use the word supermassive object?
Yeah, supermassive object would be more appropriate, I think.
But they say black hole. So now when you read astronomy books, they tell you that black holes, supermassive black holes are at the center of galaxies. Okay, well, why do I need to call it a black hole? Why couldn't I just say it's a supermassive unknown object?
Well, I would agree with you, Harry. I think we should call them that.
Okay, so the reason they're calling them black holes is because they've got a prejudice somewhere that insists that they want them to be black holes, right?
Yeah, they want them to be black holes. It's the best evidence of black hole, right? At least visually. So Cornelius, you had your flag up?
Oh, I would just say the black hole thing is just a matter of semantics and stuff like that, as far as it goes. Whether you want to call it a supermassive object that doesn't shed any light or let light shine through it or not. But no, I did.
Black hole implies GR concept.
Yeah. Okay. So basically, we're just totally opposed to GR, so we'll just change it. Not use that name, and we won't use an Einstein ring. That's fine. I'm agnostic. I don't really care.
Well, no. The point is that if you say that it's a black hole, then you're in essence interpreting it in terms of the general relativity theory, which you're assuming is correct.
Oh, okay. You're making a lot of assumptions about why I'm using the word black hole. So anyway, I didn't raise my flag about that discussion. What I raised my flag at the time was where we were talking about the various densities of the media and light changing its path, or a wave changing its path in there. And I look at it slightly differently. As you know, I don't have a particulate media. I have attention media, but in the same sense as density changes the path of waves, the attention, as I just mentioned earlier, the speed of a wave in various tensions of material, which you can tell by plucking a guitar string or whatever and stretching it, the speed of the wave varies with the tension And if you have a space that is basically of non-uniform tension, then any wave moving through it, light being a wave, then if you consider that as a wave, would also have a tendency to bend based on the gradient in tension that it was passing through. So if it was passing perpendicular to a gradient in tension, it would have a tendency to, because in a tensor material, the waves travel faster, it would have a tendency to curve towards the higher tension within the media, which is basically the space-time curvature. This is where you're saying, Harry, earlier that it's a space-time. Mainstream says it's space-time curvature, and I'm saying it is. Yes, in fact, it is. If you consider the tension, it's a tension curvature, a difference in the characteristics of the gravitational field strength, which is a measure of the tension within the media. And so whether the media is particulate or not, if it's particulate, you can talk about density. If it's not particulate, there's no such thing as density. There's just simply tension energy within it. But it's the same situation as what you're talking about, Franklin. The light will curve towards the gradient of either tension or density, however you look at it.
Well, certainly that's
Could I comment
possible.
on this? Let me comment on this. There's a big disagreement between etherists and the relativists. As I understand it, the relativity theory doesn't really give space any properties. Okay, but then in GR, there's a sort of implied property in that space is a medium. Okay, but so the properties that space have is that it changes time and space. So that you got this bending of space and bending of time, whatever, warping or whatever that means. But the space itself doesn't have any properties. Is that right?
Yeah. Right. Well, this is the case. So this is kind of why I look at tension. With tension, you don't have densities or anything like that. You don't have a particulate media, but you can have a gradient in tension within a media, which is the space-time. And within that media, then, if it's tensor, it will oscillate faster. It'll vibrate faster. If it's not tensioned, it'll vibrate slower. And if you look at it that way, ether can be. I consider it ether if it has a property of tension. It is an ether, but it doesn't necessarily have to have a particular property to it. It has to have the tension characteristic, tensionable characteristic, and the tension itself would be, in fact, like a space-time, a change in time, because we marked off time by rate of vibration or rates of vibration. Well, if rates of vibration change relative to tension of the media, then it's kind of like that's it. That's what's going on. We're changing the tension within space, and therefore the time in which reactions, activities, and experiments take place vary due to the location within the gravitational field strength you are. But
So your property that you would assign to space so you're assigning a property in addition to space, and which etherists kind of do assign properties, but they don't assign properties to space. They assign the properties to the ether. But you would.
I'm actually applying an analogous property of tension to space-time. So space-time I consider to be analogous to tensionability or relative tension.
Okay, well, that's certainly different from the way mainstream has no properties as far as I see of space.
I'm trying to bring it down to a more intuitive level than just speaking of space-time. I'm trying to give a real physical or mentally understandable or more intuitively understandable view of how things can change from location to location without any obvious cause other than like we can see something that's we really can't see tension unless we can see particulates within the media that might be spread farther apart or closer together. Then we can say, oh, that must be tension because I see the points over here are farther apart, so there must be greater tension. But if there's no particulates, if the particulates are infinitely close together, then all you really see is the tension, and you have no way of telling how tense it is unless you put a vibration into it, and that vibration will act at will resonate at a different frequency based on the tension. So I've gotten rid of the particles, and I pay attention to the tension. And I think Jeff Yee, when he speaks, will possibly get into some of this, because I think some of his is dealing with vibration of space, and I don't know if he's got a fundamental particle. I know Bill Lucas has a very, very fundamental particle. He still particulates space, I believe, into a monad. I try not to get confused with particulates because I don't feel like they're necessary. Particles are basically rays, but I'm getting way off too far in mine. But to answer your question, Harry, yes, I do attribute a property, an analogous property, really. I like the way Ian brought up the word analogous years ago, and I've always wanted to say it's analogous to tension, because that's something we can perceive, whereas space-time is a little less tangible to our minds. That's kind of all I got to say right now. You want to pass it on?
All right, so we're getting towards the end of the hour here. So let me see if I can summarize a little bit here. So we started out with this blog here, and which was entitled "The Multiverse Theory and the Ether," and this is from Abercrombie, who is with us today. And I also noticed that the person who is responding here is actually Glenn Borchardt. So that's who the GB here who's responding. So we started out the discussion about this question as to whether the ether expands everywhere, or is it limited to where the galaxies are? So, but that led us into this discussion of the Big Bang Theory. So I would say that a lot of us here are not terribly convinced about the Big Bang, but we will be getting a new piece of information, I believe, in 2021 when the James Webb Space Telescope launches, and that will be another large piece of experimental data that we can consider. Although, Harry is highly skeptical as to whether, even if the James Webb Telescope, that the theory, the evidence, empirical evidence absolutely points to the falseness of the Big Bang Theory, that theory will continue to not be falsified, that they will just come up with another gigantic fudge factor to say, oh, well, that was due to something else, and we'll still hold on to our Big Bang Theory no matter what the experiments say. So that's a possibility. But that brought us into this whole question of how we are measuring the age of the universe, and we discussed that there's some evidence for there being stars which are this 13.2 billion years old, and that's kind of like based on carbon dating kind of techniques, so we can kind of see how that works. But my own personal opinion on this is that my inclination is I don't believe that the universe had a beginning. I don't believe it has an edge. And therefore, to Abercrombie's original question, I would say that no, there is no edge to the ether bubble, and that the ether bubble extends across the entirety of the universe. And if you were to travel the universe, you could travel as far as you want, and it would look the same everywhere, pretty much. And that, so since there is no possible bubble boundary you could define, there would be no possible boundary for which you could define the ether. Although I think this question is actually kind of irrelevant, because when you get, because I think it's really only important to consider what you can observe within your within observability, I suppose. So whether if the universe was just contained in a gigantic box that God built, that for purposes of our own physics, it wouldn't matter that there is no ether outside of that, whatever that box is, because all we know for sure, and what's useful to us, is that in the room that I'm sitting in, that I think that there is an ether. And whether there is an ether a billion miles away from here or not is not relevant. And it wouldn't really add to any practical scientific knowledge, I would say. So I kind of have a philosophical problem with this entire question to start with. But once again, that's my own personal opinion, because I think the universe expands everywhere. I think it's just easier to think it did that because there are, like I said, a lot of problems with thinking it had a beginning. And then when the James Webb Space Telescope comes online, I would say, yeah, they're going to find objects older than 13.8 billion years. Another problem that I heard about is that they've done simulations on how long it takes to form galaxies, and there just hasn't been enough time to form those galaxies. It takes significantly longer than 13.8 billion years to get the structures that we observe in the galaxy. So that would be another problem with this particular timeline that they have. So after discussing the Big Bang Theory, then we kind of got into what are black holes. So Aberchecki was saying that, okay, this is proof that there are regions where light cannot propagate, and that would be black holes. So Glenn Borchardt replies that, he's skeptical that black holes exist. And I think we discussed a lot of things about, is it a black hole, or is it just a supermassive object that's dark, right? I think a black hole would specifically, you have to come, there has to be a certain amount of mass under a certain amount of radius. So a supermassive object.
Based on a prediction of GR.
Yes, based on a prediction of GR, this is like a Schwarzschild radius or something like that. So the difference between the supermassive object and the black hole is that its radius would be much smaller. So in order to be a black hole, you just have to fall below a certain radius, and any amount of mass can actually become a black hole. So if we were to take all the mass of the Earth and squeeze it down to the size of a marble, then that would be a black hole, right? It would have all the gravity of Earth. You could orbit satellites around it. And it would, and the only difference between the Earth and the black hole would be that the Earth is like 6,000 miles across, and the black hole is like half an inch across. So, but there's no way for us to know that big giant object in the middle of a Milky Way galaxy, how big that thing is. Is it really as small as a black hole, in which case it would be a black hole, or is it really, really big and it's not a black hole? Kind of hard for us to see from our vantage point here on the Earth. But that was another point that Harry made, that all this cosmological stuff is kind of hard to prove, kind of hard to run experiments. So it is largely a matter of
that's what he said, yes.
Speculation. And we can each come up with our own theories. We've heard a couple of theories here today.
I don't know how long it'll take. I don't know what he's going to tell me.
And we've got, let's see here. So Harry, I'm still here.
No, I suggest you do that.
So I'm going to have to meet you out there for just a second.
Yeah, that sounds like a good idea.
Okay, so now, we've muted Harry there. So we went on to discuss black holes. So my feeling on this is that, black hole doesn't actually provide an area where light cannot travel. We discussed what gravitational lensing looks like. So we saw several pictures of what appeared to be galaxies that were bent or distorted by the presence of these high gravitational sources. So that is what I am thinking a black hole, if it exists, it would actually do. So it wouldn't suck in light like it was mentioned, like a satellite falling down into the Earth, crashing into the Earth, literally like that. And it wouldn't be a region where light couldn't pass through. It would just be a region where light would be highly bent or distorted into what this gravitational lensing thing does. So in that way, that still wouldn't be a proof that there are these regions where light couldn't travel. In order to create something like that, I speculated that if we were able to create a region which genuinely didn't have any ether in it, that would be something that looked more like a disco ball than something that was black. It would just be some place that would reflect all light and would be completely impenetrable to any form of electromagnetic radiation, would be my speculation. So I don't think that a black hole, even if they do exist, is any evidence that there are regions where the ether couldn't exist. And like I said, once again, Glenn Borchart's opinion is that, these things probably don't exist. Maybe they're gray holes. I've never seen an actual picture of one. So that would be my comment. But I believe that brings us towards the end of our discussion today. So I thank Abhijit for bringing us this topic here. The link to this blog was put in the chat. So if you would like to go and check out what people are talking about in this blog, there's certainly a number of different topics, and you can talk about these things for a long time. For example, we just talked about this one post for today's talk, and but as Harry points out, these things that we're saying may not be very welcomed in the mainstream, which is why the John Chappell Natural Philosophy Society provides forums like this, where you can freely express whatever your opinion might be, and you need not be an expert, and we have no experts around here, pretty much. So you can say and discuss whatever happens to be on your mind, which is what this science chat is for. So thanks for everyone participating. And I'm not sure what next week's topic will be, but on January 12th, we will be having Jeff Yee will be speaking, so don't miss that. All right, but that will do it for this week's episode of the Science Chat.